Next topic, flip-flops. Put the heading flip-flops. Flip-flops are edge-sensitive devices. First, let us consider for D flip-flop. Here I am considering two D latches. Okay. Here I am having D1, that is external D input. I am giving as input for D1. Okay. Output of this one I am giving as input for this particular latch. Okay. For both the latches, you will be having two enable signals. Here I am giving external enable as the enable for this one. If you want, you can write this one as enable 1, EN1. This one as enable 2. Direct enable signal I am giving, but for this particular latch, here I am giving complemented enable. Here I am giving one inverter. The output of this one I am giving as input for this. So here, since flip-flops are edge sensitive, that means either 0 to 1 transition or from 1 to 0 transition. Okay. Only just before the transition, whatever the input you are having, so based upon that you will get the overall output, right? So that means we have to send the periodic signal. Okay. So this enable signal I am considering as periodic square wave. This is the enable signal. Okay. D input you can assume anything, no issue. D input you can consider anything, no issue. Enable signal we have to consider square wave because we will analyze only at the transitions, either 0 to 1 transition or 1 to 0 transition. That's why I have considered periodic square wave. Okay. D input you can assume anything, no issue. See, for this particular latch, enable signal is the external enable signal. Okay. Here we are giving active high, right? We are giving enable signal directly to this enable one. Okay. That means this particular latch will be enabled when enable equal to 1. When enable equal to 1. Okay. That time here next state will be equal to whatever the D input is there, that one will come. Okay. When enable equal to 0, that time what is the output here? When enable equal to 1, here next state equal to whatever the present input, whatever the input you are applying. Okay. When enable equal to 0, here next state will be equal to same as previous state, correct. So now I am writing C, the waveform for this one, Q1 signal. See, with respect to enable signal and with respect to D input, now I am determining the output. That is nothing but next state, Q1 of T plus 1. Or you can write Qn plus 1. Okay, anything okay. Qn plus 1. Okay, now, initially you can consider, see here enable equal to 0. Enable equal to 0 up to here. Right? So you can consider or assume the present state is 0. Present state is 0. As long as enable is 0, your next state will be equal to same as present state. Here I am assuming present state as 0. If you want, you can assume 1. There is no issue. Here enable equal to 1. During this period, enable equal to 1. When enable equal to 1, whatever the D input you are having, that one you will get at the output. Okay. So here I am having the waveform like this. The same change will come at the output. When enable equal to 0, next state is same as present state. Okay, present state I am assuming 0. Next, enable equal to 1. Whatever the D input you are having, the same thing will come. Enable equal to 0. Enable equal to 0. Okay, now it will remain in the same state. Just becoming 0, here the present state is 1. So it will continue in the same state. Just you are getting just before getting enable equal to 0, your present state is 1. Right? So since here enable is 0, okay, next state is same as present state. Right? Now, enable equal to 1, during this period, your D input is 0. D input is 0. So the same thing you will get at the output. Okay, enable equal to 1 here, whatever the D input is there, that same thing will come. Now, enable is 0, it will remain in the same state. It will remain in the same state. Now, enable equal to 1, here D input is 1, so output will be equal to 1. After this, enable is 0, so it will remain in the same state. So, with respect to this latch, okay, when we are giving D input and enable, whatever the output waveform we got, that is my next state. Okay, now, for this particular latch, D2 is nothing but what? Output of this particular latch. Okay, for my next operation, whatever here I got earlier, that will be the current input. Right? See, with respect to this latch, that's why I am using two notations. I am repeating once again. Okay, with respect to this latch, when you are giving these are the inputs, okay, here whatever the output I am getting, that is my next state. Okay, with respect to this latch, for this latch, D2 is nothing but output of this one. That means previous output or past output of this one will be the current input for this. That means whatever the waveform here I got, that will be when I am analyzing this particular latch, this will be the input. This particular latch will be enabled when enable equal to 0. If enable equal to 0, then 0 bar is 1. So that means this particular latch will be enabled. Okay. So here this output will be equal to D2. See here, for this particular latch will get enabled when external enable is 0. 0 bar is 1. Okay. That time this output will be equal to D2 input. Okay. If you are making enable equal to 1, that time here output is 0. That means this enable is 0. So that means this particular latch is disabled. Okay. So the next state will be equal to the same state. Okay, previous state. So now I am drawing the waveform for Q. Okay. Now observe enable equal to 0. That means this particular latch is enabled. Okay. So what is the D2? This Q1 is nothing but your D2. Q1 is nothing but D2. So when enable equal to 0, D2 is 0. That means here output is 0. When enable equal to 1, this particular latch is disabled. So it will remain in the same state. Next, enable equal to 0. Enable equal to 0, here input is 1. So output will be equal to 1. Enable equal to 0, here input is 1. So you are getting output as 1. Here enable is 1. So it will remain in the same state. Enable equal to 1, it will remain in the same state. Now, here enable equal to 0, here input is 0. That means output you will get as 0. Output equal to 0. Here enable equal to 1. Enable equal to 1. So it will remain in the same state. Here enable equal to 0. Input is 1. So output will be equal to 1. For this particular latch, when external enable is 0, that time whatever the D2 you are having, that same thing you will get. Okay. When enable equal to external enable equal to 1, that time this latch is disabled. So whatever the earlier state you are having, it will continue in the same state. It will continue in the same state. Now just observe 1 to 0 transitions. 1 to 0 transitions. See, for this overall circuit, you are having external input D in, enable signal, okay, and the final output is Q. Just observe those three waveforms only. Enable signal, D input, and final output Q. Final output Q. Now, 1 to 0 transition. Just before the transition, what is the D input? Just before the transition, input is 1. Right? So, D flip-flop for D latch, when enable equal to 1, for latch, output equal to D input. Okay. Here, for flip-flops we are talking, so output will be equal to whatever the D input you are having. Just before the transition, here input is 1, so that same thing you will get after the transition. After the transition. Just before the transition, whatever the input you are having, that input you will get just after the transition. Similarly here, 1 to 0 transition occurring. Okay, just before the transition, input is 0. Just before the transition, input is 0. Okay, that 0 will come just after the transition. Just after the transition. Similarly here, 1 to 0 transition, just before the transition, input is 1. You are getting that one as just after the transition. So here if you observe, whatever the circuit diagram we have considered, okay, we are having external input, enable signal, and external output. Okay, so here this particular circuit is operating only at the negative edges. Negative edges. Just before the negative edge, whatever the D input you are having, that one you are getting as the final output. Even though that particular input changes when your enable signal is 1 or enable signal is 0, that change won't occur. Only just before the transition, 1 to 0 transition, whatever the input you are having, that one you are getting as the output. This is negative edge. Negative edge means, see here we are having two levels, logic 0, logic 1, or bit value 0, bit value 1. Among these, which one is greater? Bit value 1, right? So here 1 to 0, 1 is nothing but 5 volts, 0 is nothing but 0 volt. Okay, so higher to lower or falling edge, both are same, negative edge or falling edge. So this particular circuit, whatever we have considered, it is operating at negative edges. Similarly, we can make it for positive edges, that means 0 to 1 transitions. just before 0 to 1 transition, whatever the input you are having, that one you will get at the output. Okay, 0 to 1 means what? 0 means 0 volt, 1 means 5 volt. So that means it is raising or positive edge, you can say. See, edge means what? Whenever transition occurring, that is nothing but edge. Okay, if it is raising from 0 to 1, that is called positive edge. If it is falling from 1 to 0, it is called negative edge, down. Higher to lower means negative, lower to higher means positive, like that. So since I have to send this periodic signal, because this particular circuit operates only at the transitions, so I have to send a periodic signal. So from now onwards, wherever enable signal in flip-flops, just in order to distinguish, I will use the symbol clock. Means you will be having clock source or square wave generator which will produce periodic square wave generator. Okay, that particular signal I will call it as clock signal. So whatever the circuit diagram here we have considered, this is negative edge triggered D flip-flop. Negative edge triggered D flip-flop. See here, in order to indicate this particular flip-flop operating at the edges, so I will use the symbol like this. This indicates edge. Okay, up to previous latch, okay, either in the decoders or latches, whenever we have considered enable, I haven't used this particular symbol. That means what? Whatever the extra signal I am giving, that particular signal, when it is active high, that particular circuit is operating. Okay, but here we are operating only at the transitions, so that means only at the edges. So in order to indicate, I am using this particular symbol. Okay, here it is negative edge, so I will put bubble. If you don't have bubble, that means positive edge. If you are having bubble, it is negative edge. So here I am giving clock signal. This is the negative edge triggered D flip-flop. Negative edge triggered means whenever clock signal transitions from 1 to 0. Whenever clock signal transitions from 1 to 0, that time only this particular flip-flop will respond. Remaining time, whatever the earlier state you are having, it will remain in the same state, like that. This is negative edge triggered D flip-flop. Okay, so inside flip-flop you will be having latches, 2 latches. For D flip-flop you will be having 2 D latches. Similarly for SR flip-flop you will be having 2 latches. JK flip-flop also internally you will be having 2 latches, like that, T flip-flop. Or otherwise, whatever we have done the analysis for one latch to other latch. Suppose we have considered SR latch and then we have converted to D latch and then to JK latch and then to T latch. Similarly, here also, first you can take SR flip-flop and then whatever the connections we have given earlier, with the same connections you will get D flip-flop and then to JK flip-flop and then to T flip-flop, like that. So whatever the flip-flop you consider inside a particular flip-flop, you will be having 2 latches. Okay, so whatever the conversion process we have considered for latches, the same thing will applicable for flip-flops. Only difference is latches are operating at level sense 2. That means only when enable equal to 1 or enable equal to 0, based upon your inputs, your output is responding. Other time, whatever the earlier state you are having, the same state you are getting. Whereas flip-flops, only at the transitions, either from 0 to 1 or from 1 to 0. Here, whatever the circuit diagram I have considered, that is negative edge. That means transitioning from 1 to 0. That means negative edge, higher to lower. Okay, that time only your next output Q of T plus 1 is nothing but D. For D flip-flop I am telling. Okay. Similarly, if you want to make it this particular circuit as positive edge triggered, what we have to do? Here I have considered for negative edge triggered D flip-flop. Okay. Similarly, we can implement positive edge triggered D flip-flop. For that, what we have to do? Yeah, we have to place one more inverter. See, here we can put one more inverter. See, here when enable equal to 1, here it is 0. Right? So for positive edge, what we have to do? We have to put one more inverter here. Then what will happen? When external enable is 0, that time 0 bar is 1. So this will be enabled, this will be disabled. When enable equal to 0. When enable equal to 1, this will be disabled, this will be enabled. Like that. So you have to put one more inverter here. Then this particular circuit will become positive edge triggered D flip-flop. Positive edge triggered D flip-flop. For positive edge, we won't represent bubble. Okay, if there is no bubble, that is a positive edge triggered. For positive edge, you have to put one more inverter here. One more inverter here. So previously in latches, I have considered Qn is the present state, Qn plus 1 is the next state. Okay. Here in flip-flops, I will use Q of T is the present state, Q of T bar as the Q of T is the present state, Q of T plus 1 is the next state. Just in order to distinguish, okay, in the latches, I have considered enable signal, whereas in flip-flops, I will use clock signal. Okay, I will change the notation. Okay, there I have used Qn is the present state. Here I will use Q of t is the present state. Okay, there I have used Qn plus 1 is the next state. Here I will use Q of t plus 1. So here it is positive edge. Positive edge means whenever clock signal transition from 0 to 1, next state will be equal to D input, like that. So whatever the characteristic equations we got for latches, the same thing will applicable for flip-flops. Only difference is latches will operate only at the level as enable is 1. Okay, whereas flip-flops will get the same particular output whenever clock transitioning from 0 to 1 or from 1 to 0. So in the question he will mention if there is a negative, if there is a bubble here, that means it is a negative edge. Whenever clock signal transitioning from 1 to 0, that time your output will be based upon your input combination. Similarly, if it is a positive edge triggered D flip-flop, that means whenever clock signal transitioning from 0 to 1, that time only your output will be affected based upon your input combination. Otherwise, it will remain in the same state. Just write the characteristic equations once again. Just write the flip-flops. SR flip-flop characteristic equation is Q of t plus 1 equal to S plus R bar Q. Whatever the equations we got for latches, the same thing will applicable here. But I will use the notation like this. Next state is Q of t plus 1. Present state is Q of t. Whatever the equations we got, characteristic equations we got for latches, the same thing will applicable for flip-flops. Okay. So here we are having SR flip-flop. S means set, R means reset. Okay. We can use this particular flip-flop for setting or for resetting. D flip-flop means, you can write down regarding D flip-flop. D flip-flop is called as data flip-flop. Because here, suppose if you want to store bit value 0, here I will give 0 to the D input. If you want to store bit value 1, I will give 1 to D input, like that. Okay. D flip-flop is called as data flip-flop. Other name for D flip-flop is delay flip-flop. Because whatever the input you are applying, that is coming for my next state. Right? So that's why here another name for D flip-flop is delay flip-flop. Data flip-flop or delay flip-flop. Here JK flip-flop, here we are giving two inputs, J and K, so accordingly the name came. Okay. Whereas T flip-flop, what is the other name for T flip-flop? Toggle. Okay. T flip-flop is called as toggle flip-flop. Toggle flip-flop. Because see, if you make T equal to 1, then what will be the characteristic equation? If you substitute T value 1, then what will be the characteristic equation? Q bar. 1 XOR Q of T, that is Q of T bar. That means if you are making T equal to 1 permanently, then whatever the output you are having, okay, that output will be complemented. Suppose initially if it is 0, 0 will become 1, next 0, 1, like that. Okay. So continuously it will be complemented, right? So that particular phenomena is called toggle phenomena. If T equal to 1, then next state will be equal to complement of present state for each and every clock's edge. If you are considering positive edge, that means for every positive edge of the clock signal. If you are considering negative edge, for every negative edge of the clock signal, like that. For every negative edge of the clock signal, if you want, you can write for negative edge. Assume the given flip-flop is negative edge triggered flip-flop, like that. Okay. If T equal to 1, then the next state of T flip-flop will be equal to complement of present state for every negative edge of the clock signal. Within brackets, you can write positive edge of the clock signal. If you are considering that particular flip-flop is positive edge triggered, then only at the transitions it will be complemented, like that. Okay. As per gate exam point of view, you have to remember the characteristic equations. Okay. If you remember these characteristic equations, okay, he will give the questions like, he will give one particular flip-flop and he will give some additional logic gates and he will ask what is the overall circuit. Okay. If you remember these equations, it is easy to answer those questions. Write down the question. A sequential circuit using D flip-flop and logic gates is shown in the figure where X and Y are the inputs and Z is the output. The circuit is dash. Write down the four choices. He has given the circuit diagram like this and he has given the four choices. He is asking what is the overall circuit. First write the characteristic equation of given flip-flop. Here given flip-flop is D flip-flop. Okay. First write the characteristic equation of this one. That is Q of T plus 1 equal to D. First write the characteristic equation of given flip-flop, that is Q of t plus 1 equal to D. Okay, now find out D value. Find out D value. Here x bar Q of t plus y into Q bar. So initially we have written characteristic equation of D flip-flop, that is Q of t plus 1 equal to D. Now find out the D value. Here I am having bubble, that means x bar, other input is Q. Okay, next here y, other input is Q bar. X bar Q plus y Q bar. Now verify option by option. Here two options are given, SR flip-flop, x value, y value are different. Okay, if you are having x value and y value are different, okay, you never get SR flip-flop characteristic equation, because SR flip-flop characteristic equation is S plus R bar Q. Okay, here you are having that kind of format, but here you should have only like this term. Okay, that means straight away you can eliminate option A, option B. It can be one among these two. It will be JK flip-flop. Just write the characteristic equation of JK flip-flop and then check with the given options. JK flip-flop characteristic equation is Q of t plus 1 equal to JQ bar plus K bar Q. JQ bar plus K bar Q. Equate like this. Q bar you are having, that means y equal to j. Next, equate these two, x equal to k. That means option D. Option D is the correct answer. Next question, draw this circuit diagram. Tell me this particular circuit, which particular flip-flop this? Yeah, T flip-flop. See, first write the characteristic equation of given flip-flop, that is Q of t plus 1 equal to D. Okay, here D is what? X exclusive or Q. X exclusive or Q of t. So you are having characteristic equation of T flip-flop as Tx or Q of t. That means if X equal to T, then this particular circuit will act as T flip-flop. It is a T flip-flop. Next question, consider T flip-flop here and use same exclusive OR gate, same connection, just in the place of D, consider T flip-flop. What will be the resulting circuit? Instead of D flip-flop, consider T flip-flop. What will be the resulting circuit? Here I am considering T flip-flop. Okay, first write the characteristic equation of T flip-flop, that is Q of t plus 1 equal to T exclusive OR Q of t. Always we will write the characteristic equation of given flip-flop. Okay. So Q of t plus 1 equal to Tx or Q of t. Now what is T? T is nothing but X exclusive or Q of t. We know that exclusive OR operator satisfies associative law, right? That means you can perform exclusive OR operation on any two variables first. Okay. So I will perform on these two variables first. If both are same, like if this is 0, this is 0, or if this is 1, this is 1, like that. Here it will be 0. X exclusive or 0. What is this value? Right? That means if X equal to D, then Q of t plus 1 equal to D. That means this particular circuit is D flip-flop. If X equal to D, then this circuit is D flip-flop. You don't need to remember how to convert one particular flip-flop to other. Okay, he will give some particular flip-flop and he will give some logic gates and he will ask what is the overall circuit. First, you have to write the characteristic equation of given flip-flop and then whatever the inputs you are having, try to find out and substitute, and from that you will get the resultant simplified equation and then check with your known characteristic equations. Here we are having 4 flip-flops. Whatever the simplified equation you are getting, just check with those 4 flip-flops characteristic equations. From that you can choose the correct answer. Okay. Next question, in the figure shown below, the initial state of Q is 0. The output is observed after the application of each clock pulse, full stop. The output sequence at Q is dash. Draw the circuit diagram. He has given JK flip-flop. Here he has given the circuit diagram like this, JK flip-flop. Here J equal to 1, K equal to Q bar. Okay, first write the characteristic equation of JK flip-flop. That is Q of t plus 1 equal to JQ bar plus K bar Q. Substitute J and K values here. So J is 1, that is Q bar. See, K is Q bar, that means K bar will be Q. So here Q into Q is Q, here Q bar. So Q plus Q bar is 1. That means for every, here he has given positive edge triggered clock signal. That means for every positive edge of the clock signal, here output will be 1. That means option C. For this question, even if it is negative edge, also same answer. See, whether the circuit is operating at positive transitions, that means 0 to 1 transition or 1 to 0 transition, for that he will indicate clock signal, whether it is positive edge or negative edge, like that. So whatever the equation, characteristic equation we are writing, this particular equation is valid only at those transitions. Okay, if we mention here it is positive edge, means for every positive edge of the clock signal, like that. If it is a bubble, if it is there, means negative edge, like that. For remaining cases, whatever the state, earlier you are having the same state, it will continue. That is the only difference between latch and flip-flop. Here flip-flops will respond only at the edges, either negative edges or positive edges. Next question, the clock frequency applied to the digital circuit shown in the figure is 1 kHz. Is 1 kHz. Full stop. If the initial state of the output Q of the flip-flop is 0, then the frequency of the output waveform Q in kilohertz is dash. Draw the circuit diagram. He has given the circuit diagram like this. He has mentioned the clock frequency of the signal is 1 kHz and he is observing the output at Q. Okay, initial state is 0. Okay, now he is asking the frequency of this particular waveform at Q in kilohertz. See, regarding the output frequency, I will mention little later. Okay, you follow the previous procedure. Okay, first write the characteristic equation of given flip-flop. Here it is T flip-flop. First write the characteristic equation and then find out here T value and substitute and try to get the simplified equation. After that, I will explain for regarding this particular output frequency. Up to there, it is a similar procedure. See, apparently this particular circuit or question, may seems to be like different question, but up to now, whatever the procedure we have done, the same procedure will applicable. Only after that step, we have to do one more step, that's all. First, you have to write the characteristic equation of T flip-flop and then find out T and substitute there and simplify it. See here, first write the characteristic equation, that is Q of T plus 1 equal to T exclusive or Q of T. T exclusive or Q of T. Now, here what is the T value? See, by looking at this particular logic gates, it may seems to be like difficult to get the expression for T. It may take more time. But here just observe, look at the inputs. Here you are having exclusive OR gate, here you are having exclusion OR gate. Exclusive OR gate, exclusion OR gate. Okay. See, here what are the inputs you are applying? Q, other input is Q bar. You are giving Q and Q bar as the inputs for exclusive OR gate. Similarly for exclusion OR gate also. Right? So that means if this is 0, this will be 1. Or if this is 1, this will be 0. Like that. Right? So here exclusive OR and exclusion OR both are complement to each other. Right? So here you are getting only two combinations, either 0 1 or 1 0. For that combination here exclusive OR will produce output as 1, exclusion OR gate will produce output as 0. Okay. Here NAND gate, one of the input is 0, output is 1. If at least one of the input is 0, output is 1. Okay. That means T value is 1. It may be looking like this, you are having very big circuit. Difficult to get the expression for T. But just look at the inputs. What are the inputs he has connected? Okay. Up to here, is it clear? Okay, I am repeating once again. See here, exclusive OR gate, you are having two inputs. One input is Q, other input is Q bar. Similarly, for this exclusion OR gate, you are having the same inputs, Q, Q bar. Okay, that means if Q is 0, Q bar will be 1. Here you will get only two cases like 0, 1 or 1, 0. If Q is 0, Q bar will be 1, or if Q is 1, Q bar will be 0. Only two combinations you will get. Okay. Exclusive OR gate, exclusion OR gate, both are complement to each other. Okay. for these two combinations, for 0 1 case or 1 0 case, exclusive OR gate will produce output as 1. Okay. For those two combinations, here you will get output as 0. Okay. Here NAND gate, one of the input is 0, output will be 1. Okay. So that means here substitute t value 1 XOR q of t, that is q bar. So that means here it is a negative edge triggered clock flip-flop. Okay. That means for every negative edge of the clock signal, output will be complement that of present state. Next state output will be equal to complement of present state. Okay. So here first I am drawing the clock signal. This is the clock signal I am considering. This particular flip-flop will respond only at the negative edge of the clock signal. So here I am considering 1 to 0 transitions. 1 to 0 transitions. Now, initially he has mentioned Q is 0. Initially it is 0. Initially Q is 0. Now, here we are getting negative edge of the clock signal. That means 1 to 0 transition. Okay. So only after the transition, here what is the characteristic equation you got? Q of t plus 1 equal to complement of present state. Just before the transition, here you are having 0. Okay. So it will be complemented to 1. After the transition, it will be 1. And it will remain in that state till you are getting one more negative edge. Okay, here I am getting negative edge. Just before the transition, here input is 1. Okay, so it will be complemented to 0. Just after the transition. And it will remain in that state till you are getting one more negative edge. Okay, here it will be 1. Okay, so just observe. Here time period of this particular clock signal is nothing but raising edge to raising edge. That is called as time period, or falling edge to falling edge. That is also called as time period. Yes or no? Raising edge to raising edge or falling edge to falling edge. That is the time period. Here if you observe, for one particular time period of the clock signal, your output is staying at 1, and similarly for other time period it is staying at 0. So that means here you are having t, here one more t. That means this particular waveform will repeat, okay, this particular fashion having the period 2t. Okay, that means from here you will get frequency as 1 by 2t. Reciprocal of this one, fq equal to 1 by 2t, where 1 by t is the clock signal frequency, f, divided by 2. F he has given 1 kHz. 1 kHz divided by 2, that is 0.5 kHz. Since he is asking the answer in kHz, answer is 0.5. Answer is 0.5. Next topic, resistors. You can write down. Regarding flip-flops, I already mentioned. D flip-flop we are using for storing 1 bit of information. Okay, if we want to store multiple bit of information, we will use multiple D flip-flops. You can write down. If we want to store multiple bits of information, then we have to cascade multiple D flip-flops. Group of D flip-flops is known as resistor. Next point, an n-bit register consists of n D flip-flops and stores n bits of information. Next point, if the resistor is having the capability of shifting the information, then it is known as shift register. So based on the direction in which the shifting is taking place, we can classify shift registers into two categories. One is left shift register, another one is right shift register. So based on the direction in which the shifting is taking place, either to the left hand side or to the right hand side, based on that we are having two types of shift registers. One is left shift, another one is right shift register. Draw the architecture. Suppose for 4-bit case I am considering. So this is the resistor. Okay. So here left shift. That means here shifting will take place like this, left hand side. Here shifting will take place toward right hand side. So based on the direction in which shifting is taking place, either to the left hand side or to the right hand side. So accordingly we are having two types of shift registers. Next one, we can classify the shift registers into 4 categories based on the way we can give the inputs into the register and based on the way we can access the outputs from the register. So based on that, we can classify into 4 categories. See here, you are having the shift register. Either you can consider left hand side or right hand side, no issue. Okay. Here in this particular shift register, okay, how we are given the inputs, either bit by bit serially or parallelly, all the bits at the same time, okay, or okay, that is the input side. Similarly, output side, whether we are taking bit by bit serially or we are taking all the bits at the same time. So accordingly, we will be having 4 categories. First one is serial in, serial out shift register. That means here input we are sending serially bit by bit. Similarly, we are accessing the output bit by bit serially. For the time being, I am considering right shift register. You can consider left shift also. There is no issue. Here, I will give the input serially. This is serial input. Okay. Here, I will access the output serially. That means bit by bit. Serial output. See here, I am giving the input bit by bit and I am accessing the output bit by bit. Next one is serial in, parallel out shift register. Serial in, parallel out shift register. Here I am giving the input serially, bit by bit, but here I can access the output parallelly. Output we can access parallelly. Serial in, parallel out. Here we are giving the input bit by bit serially. Here we are accessing the bit by bit output serially. Okay. Whereas here input I am giving serially into the register and I am accessing the output parallelly. Internally shifting will take place like this. You can assume left shift also, there is no issue. For the time being I am considering right shift. Similarly, draw other 2 configurations. Parallel in, serial out, shift register. Here we are giving the inputs parallelly into the each flip-flop. Okay. And shifting is taking place like this and we are accessing the output serially. Parallel in, serial out, shift register. Last one is parallel in, parallel out. So here we are giving the inputs parallelly. Okay. The moment you will give the inputs and you will apply the clock signal, you will get the outputs. Okay. Whenever you don't want to load any data, that time you can, if you want, you can make it as for shifting operation. So here if you observe, among here you are having 4 configurations. Serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Just observe these configurations. Which one is the simplest one? Parallel in, parallel out is the fastest one. I am asking about simplest. Simplest means number of connections are less. See here you are having one input line, one output line. Okay, this is the simplest one. Of course, you will be having clock signal. For the time being, I haven't represented that one. Okay, here you are having one input line, one output line. This is the simplest one. Okay, whereas here you will be having, see, multiple lines you are having inputs. Okay, similarly multiple output lines. Okay, so here if you observe, this is the fastest one because the moment you are giving the inputs, after applying the clock signal, you will get the outputs. Okay, parallel. This is the slowest shift register. This is the simplest one, simplest shift register, but it is the slowest one. This is the fastest shift register. Fastest shift register. Just observe other 2. Serial in, parallel out. Here parallel in, serial out. That means we can use shift registers for converting serial input into parallel output. Similarly, parallel input into serial output. These are the applications of shift registers. Whenever, see, we will store some particular information. Okay, that particular information if we have to give to as an input for some other circuit. Okay, if there is any delay, then with the help of serial in, serial out, we can use this particular shift register just in order to slow the process. If you put the number of flip-flops, okay, that many clock cycles it will take in order to shift the information. Okay, so after that we will give this particular information as input for some other. Okay, if some particular devices or circuits, okay, are at faster speed, okay, then we will use this one parallel in, parallel out. We will give the inputs. After applying the clock signal, we will get the output. Okay. Similarly, we can use shift registers for serial to parallel conversion and parallel to serial conversion. Here you will get the questions. He will give one particular shift register and with the help of some logic gates. Okay. Initially, there will be some particular state is there. After applying how many clock cycles you are getting the same state. Like that, you will get the questions. He will mention how the shifting is taking place, whether right hand side or left hand side, like that. Write down the question. A 4-bit serial in parallel shift register is used with a feedback as shown in the figure. Full stop. The shifting sequence is, write down the sequence. He has given the sequence like this: QA, QB, QC, QD. That means right shift is taking place. He has given the shifting sequence like this. If the output is 0 0 0 0, then the output repeats after dash clock cycles. You can draw this circuit diagram. Here he has given 4-bit serial in parallel shift register. The shifting is taking place like this. Okay, and here see serial in parallel. Input is coming serially, but outputs we can access parallelly. Okay, so QB QD he has given as input for exclusion OR gate. That output he is giving as a serial input. Now the question is, initially you are having 4 zeros. After applying how many clock cycles, you will get the same status. So here I will consider clock signal. I will consider serial input. Serial input is QB exclusion or QD. QB exclusion or QD. Here 4 outputs are QA, QB, QC, QD. Okay. So here we are having 4 bits serial in parallel shift register. Serial input is QB exclusion or QD. And here we are having 4 outputs QA, QB, QC, QD. And here I am representing the clock numbering. Okay. Here if you observe, it is a positively triggered. So that means whenever, see, you will be having clock signal periodic waveform. Okay. Whenever clock signal is transitioning from 0 to 1. Okay. That numbering I will give. First clock pulse, second clock pulse, third clock pulse, like that. Whenever 0 to 1 transitioning occurring, that numbering here I will put. Okay. So when there is no clock signal applied, he has mentioned initial status is 4 zeros. Initial status is 4 zeros. Serial input is what? QB exclusion or QD. Just observe these 2 bits. See, exclusion or is nothing but what? For 2-bit case, if both the bits are same, output is 1. If both the bits are different, output is 0. Right? So here both the bits are zeros. So output is 1. Okay, that means initially before applying the clock signal, we are having 4 zeros. Here we are having logic gate. Okay. Logic gate means the moment you are getting the inputs, here it will get output. Okay. Now I am applying first clock pulse. First clock pulse means first time I am getting clock signal 0 to 1 transition. Okay. That time, whatever the serial input is there, that will come here. These 3 bits will get right shift. Because here he has mentioned the shifting sequence like this. So these 3 bits will get right shift. After applying the first clock pulse, that means first time 0 to 1 transition, whatever the serial input is there, that will come here, and whatever the bits here you are having, that will shift right hand side. Because here he has mentioned the right shift operation. See, initially you are having 4 zeros. Okay. When there is no clock signal. Okay. Here serial input is what? QB exclusion or QD. Exclusion or operation means what? For 2-bit case, if both the bits are same, output will be 1. Okay. Here QB, QD values as zeros, 0. So output is 1. Okay. Now I am applying first clock pulse. First clock pulse means first time I am getting clock transitioning 0 to 1. Okay. That time, whatever the serial input you are having, that bit will come here. Sorry, this is 1. Okay. Yeah, this is 1. This 1, and these 3 bits will get right shift. These 3 bits will get right shift. Now, here 0 0, output is 1. Next, second clock pulse I am applying. This 1 will come here. These 3 bits will get right shift. Next, here 1 0. 1 0 means these 2 are different. Output is 0. Next, third clock pulse. This 0 will come here. These 3 bits will get right shift. 1 1 0. Next, 1 0 means different. Output is 0. Fourth clock pulse. This 0 will come here. These 3 bits will get right shift. 0 1 1. 0 1 1. Here 0 1 different. Output is 0. Fifth clock pulse. This 0 will come here. These 3 bits will get right shift. Next, 0 1 means different. Output is 0. Sixth clock pulse. This 0 will come. These 3 bits will get right shift. So we have started with 4 zeros. We are getting the same status after applying 6 clock pulses. Answer is 6. See, second cycle, just before applying this one. Okay, here 0 0. Both the bits are same. Output is 1. Right? So I am applying second clock pulse. Here serial input is 1. That will come here. These 3 bits will get right shift. 1 0 0. Here I am having 1 0. These two are different, so output is 0. Okay, third clock pulse, this serial input will come here, these 3 bits will get right shift, like that. Okay, similarly the same operation will take place. Okay, for each and every clock pulse, you will check these 2 bits. If these 2 bits are same, output is 1. Or if these 2 bits are different, output is 0. Okay, so that serial, that whatever value here you are getting, that will be before applying next clock pulse. Okay, after applying the clock pulse, whatever the status here you are having, that will come here, and these 3 bits will get right shift, like that. Okay, similar question you can try later as a homework. Just draw the circuit diagram. Similar question it will be. Similar question. For this question, initial status is 1010. After applying how many clock cycles, you will get the same status. Here, serial input is what? Here first you are getting QC XR QD. After that, XR with QB. That means serial input is, here in this case, serial input will be QB exclusive or QC exclusive or QD. QB exclusive or QC exclusive or QD. Okay, similar question, you can try this particular question later as a homework.